Today I want to talk about something very interesting. It's about the development of physics, essentially how it's today, the level that quantum mechanics is. If quantum mechanics is a theory that's complete, or if there's something that's missing there. There is a question that exists today. There is the models that affirm that the theory is complete, that there's no problems there, that just follow what's established, follow the Schrödinger's equation, you make a kind of extension of that to the classical settings. With that, you have no problem at all with the system is complete, the explanation is complete, there's no problem. Even today in the more professional settings, like for example in quantum engineering, when people study quantum computers and work in quantum computers, they take this approach like decoherence as being the standard, and that's no problem, they're all there. But it's not a full consensus in the scientific community. We have, for example, Penrose that points out that is a problem there, that actually the system don't work, and as I saw in others examples that some people point out, you have an internal contradiction between the way you approach the measurement and these things about the probabilities, the transition that occur there, and traditional Schrödinger's equation that's a full linear and completely predictable equation, deterministic equation, there's no problem there. But in the actuality, when you to explain how what you see actually in the experiments and the measurements go beyond that. And the paper of Schrödinger himself, you have this, is shown that there's a problem, what many people take as something that's very cool, very interesting, the Schrödinger's paradox of the cat that both alive and dead, but actually it's a problem. It's a really problematic thing. It's not something to be celebrated, but means that the theory is incomplete. You can say that's almost like a singularity, but it's a physical singularity, a conceptual singularity. You cannot have something like that. It's kind of absurd. But people took what Schrödinger explained and the paper of Schrödinger and follow a very strange line of thought in which they try to use the decoherence and the better understanding of the dynamics of entanglement to extend Schrödinger and to make the cat, the idea of the cat and alive and dead, to be something that makes sense in the way that as kind of a tensorial product between the various parts of the wave, and as the information of that the system kind of leak out to the environment, there is a process of creating orthogonal spaces, orthogonal phases. These orthogonal lines become kind of separated, and the experience of the classical world is this experience of these lines that kind of survive when you have this process of the end of the information leak out to environment. This is the approach, but you preserve the problem. The problem continue to be there. You have a cat that's alive and dead, and because in the same place is not like the main world, for example, that believe that reality is splits, and it's a very absurd approach. But in the same place you have these two lines, for example, the cat alive and dead, and this is still a problem. The correct approach would be to look to what we see. We see a phenomena that's not explained by Schrödinger. It's a limitation of the theory. And you have a limitation of the theory. What good science is, it's historically, you must understand the process, the phenomena. And by understanding the phenomena, you should connect this phenomena, this process, to some physical quantity that's associated there. And this should be the lens to look to this problem, and not the way that's approached today. The way it's approached today is very, very problematic. It's not a good approach at all. And more than that, we not just should approach this, but also something that's true. as Penrose said again, as Einstein before said, there is a division between classical and quantum mechanics. There is, of course, all the bodies, every body that exists in the universe is composed by the fundamental excitations in the quantum field as elements. In other words, everything is composed by quantum elements. This is a fact. But there is some process of emergence of the behavior of the dynamics that we say that dynamics of the classical system. There is a real emergence, there is a real difference. Like exist two realms that are separated, they're not the same, there is a real difference there. This is a fact. And some kind of property, the process of acquire a property should make this difference, should create this difference. That is the way that we have, for example, that's a basis to think about that, is the error fast. As error fast show that when you take the limit, you aggregate more and more elements, more and more quantum elements. There's a process, and there's emergence. As the expected value converges to what you measure in the classical system, there is really something there. There's aggregation more or more elements. So I think that the correct approach is take this as inspiration from error fast and try to find the qualitative aspect of that, because error fast just explain the quantity effect, the fact that there is a preservation of the internal superposition in a classical system that's different from a quantum system, means that there's something about we aggregate more. When you aggregate more and more elements, there is some kind of threshold that when that you pass this value, there is a transition and a new dynamics emerges there. New dynamics that's different from what we have before. I think here we have a very interesting clue what can be the solution. When we think about the information, the Holovos theorem shows us this, that you have information that's about interaction. And this information about interactions is ON. Its information is linear, but you have an information that's not it's exponential beyond this. This internal information, that don't make any aspect interactions, but there is this other part of the information. It's almost an internal information superposition, can say. I believe that's possible, that the explanation of the different dynamics is come from this part. The other part that is about interactions grows linearly, there's no general aspect there different, but the part that's connected to this that grow exponentially can be the cause in some way of the different dynamic. So in many ways, I think the correct approach is the inverse to what is the most canonical way of approach today. Because as decoherence, that the standard approach for people today to have a solution to this problem, the information is kind of leaking of the information to the environment. There is the selection of these lines in the wave function. And this is what it is, the classical state. But I think it's to the contrary. Actually, a classical body is a body that contains the information. The information don't leak at all, because the experiment actually say this to us. Is this what the experiment say direct to us? Because when you interact with the classical body, you just extract information from the classical body, but then information of superposition is preserved, is there. It's preserved. There's no formation of the state collapse and formation of eigenvalues, transition to eigenvalues, anything like that. This is different, very, very different. But when you have a quantum system, that system exists a transition to an eigen state. In other words, there's something in the body. The classical body don't leak information. It's to the contrary. A classical body contains the information. So I think that's essentially this should be the approach. This should be the approach to resolve this problem. And the problem is there. The idea that the problem is not there, that you could make this artificial extension of Schrödinger to a realm and preserve the gap that's both alive and dead is not the correct approach. The correct approach is to find something that relates to the measurement, some physical quantity related to this process, and with this derive a theory, derive a hypothesis.